Good day everyone. So we will now have the continuation on the discussion on the second condition of equilibrium. So this time we will discuss the resultant moment. If there are two or more forces that are acting to our moment arm, so we will determine the resultant force or the summation of force. And in this type of problem, the summation of force is not equal to 0. So here I have two forces. So we have force P and a force F acting on our pole. And the pivot here on this problem is the point A. So it means if I'm going to determine the net moment on this problem, I will use this formula in which the summation of moment at point A is just equal to the moment of at point A due to force P, so this one, plus the moment of point A due to force F. Since force F and force P is in the diagonal position, means it is in between quadrants, so we expect we will get the components of force P and we will get the components of force F. So to solve for the summation of moment at point A, we will have the sum of the moment of Px plus the moment due to force Y, and we will also get the moment due to Fx, and we will get the moment due to Fy, and we will get the sum of this, and we will determine what is the net rotation of this pole due to these forces. So let's try to solve it. So first, we have to identify the force F and its moment arm or the lever arm. So the moment arm of force F is 12 feet, while for force P, the moment arm of force P is 18 feet. I will place this diagram into an XY axis so that we can name them as PX or PY. So here, this is the origin, which is in our pivot, and that is the x-axis, and this is our y-axis. So the component of P is Px, that is along x or negative x, and Py, which is along the negative y. So since we are trying to solve for the components of Px and Py, we have to place this 45 degrees near to the origin of the force, and this is the case. So this is 45, this is also 45. So let's try to solve now for the moment of Px and Py. Now for the moment of Px, that is Px times its moment arm, which is in this case that is 18 feet. For the moment due to Py, that is also Py times the moment arm, that is 18 feet. But from our previous discussion, since Py is parallel to our moment arm, so the moment due to Py is equal to 0. So we are just going to solve the moment due to Px. And Px here, so this is Px, and that is the adjacent of 45, so that is P cosine 45 times its moment arm, and P is 50 pound, so that is 50 pound cosine 45 degrees times 18 feet, and that is 35.36 pound times 18 feet. So the moment due to Px is 636.4 pound-feet, and the direction of that, if you will look, this is the pivot and this is Px, so it will make to turn into a counterclockwise direction, so that is CCW or positive 636.4 pound-feet. Now for the force F, so we will get the components first of our force F, so that is Fx, and this is Fy. And since this is in the diagonal position, so we have to get the angle of these forces. So we have the slope here, so we will get this angle. So I will use the tangent, so arc tangent 3/4, the answer is 36.87 degrees. So this angle is 36.87 degrees. Since this is 36.87, I have to place it near to the origin of the force, so this time this is also 36.87 degrees. So let's try to solve now. So we have the moment due to Fx, so that is Fx times the moment arm, and the moment of Fy, that is Fy times the moment arm. Since if we will look again, Fy is parallel to our moment arm, so it means this is also 0. So we will just solve again for the moment due to Fx. Let's solve it. So Fx is also the adjacent of 36.87, so that is cosine. So that is 80 pound cosine 36.87 times 12 feet. So the answer for that is 64 times 12 feet, and that is 786 pound-feet. And if you will look for Fx, this Fx will make our pole to turn into a clockwise direction. And since this is a clockwise direction and we have to get the summation of moment, I have to use the sign which is negative 768 pound-feet, since we have to get the summation of all this moment. So let's proceed now to our summation of moment. So that is the summation of moment of MA due to PX, moment on A due to PY, moment due to FX, and moment due to FY. And since moment due to PY and moment due to FY is 0, so we will just add these two. So that is 336.4 pound-feet, and that is positive. And for moment of force due to Fx, and that is negative 768 pound-feet. So the answer is negative 131.6 pound-feet, and the direction of that, so since this is negative, so we know this is in a clockwise direction. So instead of writing negative, our answer now for the summation of moment due to these forces on our point A is 136.6 pound-feet in a clockwise direction. So let's try to solve now this same problem that we have discussed in our previous lecture. This time we will use the product of vectors. So this is what we called the vector analysis or vector solution of this problem. So here, instead of 100 Newton, since this is a product of vectors, we will use the ijk as our direction. So we will indicate now the direction of our forces and our moment arm, since these two are both vectors. So here, instead of 100 Newton, we will name this as 100 Newton negative j hat. Since our force is going downward, so you have to imagine that there is an axis for force here. That is, this is x and that is y. And since we can see that the force F is going down, going to negative y, so that is negative j. Now, for the moment arm, since the moment arm always depends on our pivot, so this is our pivot, that is our origin, and this is the x-axis, and this is the y-axis, and we can see that the moment arm is from the pivot to the line of force, so it means that is positive I. So that is 2 meters positive I hat. And if we will now compute for our moment of force using the vector analysis, we will have displacement first, or the moment arm, cross force. This is always how we will solve for the product of vectors of moment. So moment arm first before the force. So that will be 2I hat meters. That is the value of and the direction of our moment arm, cross negative 100 j Newton, because this is negative. So that is, if we will distribute that, so that is negative 100 j Newton. You can have two solutions here. It's either you will multiply first the value, so that is 2 times 100, so that is 200. And we will now include the sign to the direction, so that is your thumb should be pointing on positive I and your forefinger should be pointing on downward, because that is negative j. So the direction of our 200 meters here is negative k. And the unit of that is Newton meter. So instead of meter Newton, we will write Newton meter. So the other solution, it can either be, we will place the sign to the magnitude, so that is positive 2 times negative 100, so that is negative 200. And so we will have now the positive sign or positive direction, so that is I, and cross j, positive j, so that is going up. So it means the answer is k. And still, the answer is negative 200 k hat Newton meter. This is how to solve for the moment of force using the vector analysis or vector solution. So let's try to solve another problem. So this is the problem we have solved before. So the line of action here, so this is the line of force and this is our moment arm. If we will solve for the vector analysis, we have to get the direction of our force and direction of our moment arm. So first, we will get the direction of our 50 meters. So again, you have to imagine there is an own axis for our force. So if this is y and this is x, our force is on negative x-axis. So that is 50 Newton negative I hat. And for our moment arm, that is always depends to the position of the pivot. So this is x-axis, this is y-axis. So our moment arm is below the origin. So that is negative j. So our moment arm here is 0.75 meter negative j hat. Now, if we will get now the product of these two vectors, so we will place first again the moment arm. So that is moment arm cross the force. And that is the moment arm is negative 0.75 j hat. So that is our moment arm cross negative 50 Newton. So we will multiply first the magnitude. So that is negative 0.75 times negative 50. So that is positive 37.5. Now, if we will multiply now the direction, okay, since we already included the sign to the magnitude, so that is negative times negative, so that is positive. So for the product of the direction, so our thumb should be pointing upward, so that is positive j, and our four fingers pointing on positive x, so that is negative k. So our palm is facing on negative k. So the answer here is 37.5 negative k hat or negative 37.5 k hat Newton meter. So try to solve another problem which is we solved before. So we have two forces here again. So since this is components, we will solve the moment of force due to Fx and the moment of force due to Fy using the vector solution. So for the vector solution, so we have the moment arm first times the component of our force, which is F sine theta. So the direction of moment arm here is 2 I hat meters and the force is 100 Newton sine 30 and the direction Fx is going to negative I hat. And we know I cross I is just equal to 0. So the moment of force here due to Fx, as we proved, that is 0. Now, the moment of force due to Fy is equal to, so that will be d times F cosine theta. So that will be 2 meters I hat and Fy is going down. So that is negative j hat and that is 100 Newton cosine 30. And that is positive 2I meters times negative 86.6 j hat Newton. So if we will multiply the values first with the sign, so that is 2 times negative 86.6, so that is negative 173.2. If we will get the direction, so that is, so your thumb is on positive I, so that is going to the right, and your four fingers will be going up, so that is positive J. So your direction is outward, so that is K. So that is negative 173.21 K hat. So this is now the moment of force due to Fy. And we will get the summation of moment. So moment of force due to Fx and summation of moment due to Fy. So the summation of moment due to Fx is 0. And the summation of moment due to Fy is negative 173.21 K hat. And the answer for the summation of moment is negative 173.21 k hat Newton meter. So for the product of vectors, there is another solution in which we can use the matrix or the determinants. So if you will remember, we have discussed these determinants in our previous lecture. So this is the product of vectors. So let's try to solve the same problem using determinants. So here, this is the table. Forget the moment of force using determinants. So that is R, the moment arm cross the force, is equal to the matrix of IJK, Rx, Ry, Rz, and Fx, Fy, and Fz. So it means we have to get the moment arm into this format, which is rxi hat plus ryj hat plus rzk hat. This is the Cartesian form of our moment arm. And the same for our force, we will get the Cartesian form of our, so which is fxi hat, fyj hat, and fj k hat. Now, if you will look here to our diagram, we can see that our moment arm is just in x-axis. So it means if this is the pivot, our moment arm here is 2 meters on positive x-axis. So we have the value only on I hat. And for ry and rz, that will be 0. So this is now the answer. So our moment arm is 2 meters I hat. Now, for the force, since this is in diagonal position, so we have value of fx I hat plus fy j hat for the direction and 0 for z. So, to get the force of F, that is F sine theta I hat plus F cosine theta j hat. And we have the answer of this in our previous problem. So, that will be, so since Fx going to negative x, so that is negative 50 I hat. And our Fy is going downward, so that is negative 86.6 j hat Newton. So, let's try to solve the product of these two vectors using this matrix. So remember, if you will multiply, if you will use this is the pattern. Okay, so that is R cross F. So this is the moment arm and this is the force. So we have to cover first for the I. So that will be Ry times Fz minus Rz times Fy, and that is I hat, minus, so you have to cover the J, Rx times Fz minus Rz times Fx, and that is J hat, plus you have to cover the K hat, so that is Rx times Fy minus Ry times Fx. And let's try to solve this. If I will solve now, so this is the moment, so that is R cross F, and that it will be the matrix, so that is I, this is J, and this is K. For the second row, it should be the value of our R. So we can see here, we only have the value for I, so that is 2 meters. And for J, that is 0. And for K, that is also 0. And for the third row, that will be the components of our F. So that is negative 50. That is I. Then negative 86.60. That is J, and 0 for K. So let's try to solve now. So that is for, let's cover the I first. So that is 0 times 0, that is 0. 0 times negative 86, that's still 0. So that is I hat. Then minus, let's cover the J. So that is 2 meters times 0, so that is still 0. Then 0 times negative 50, that is still 0. And that is J hat. Plus, so that is 2 times negative 86.6, that is negative 173.20. That is, and 0 times negative 50, that is 0, and that is K hat. So here, the final answer for the product of R cross F, so this is our moment at point O, so that is negative 173.20, and the direction is K hat. And do not forget the unit. So the unit of our R is meter, and the unit of our force is Newton. So that is Newton meter. So instead of meter Newton, so to properly write it, so that is Newton meter. So this is the answer for our moment. So let's try to solve another using the vector analysis. So determine the moment of a force about a pivot O. Express the result as a Cartesian vector. So this is a force. So that is the direction of the force. And the moment arm is always the distance from our pivot to the point of our force, so which is at point B. So the distance from point O to point B is 4 meters, and that is our moment arm. So the moment arm, so the formula for moment arm, so that is Rxi hat, Ryj hat plus Rzk hat. And to get the force, that is Fxi hat plus Fyj hat plus Fzk hat. But since the given here is just the magnitude, we will use the formula force that we have discussed previously, in which that is force is equal to the magnitude of the force times the unit vector. And to get these unit vectors, we will use a position vector. This position vector, which is parallel to our force. And this position vector is also the same direction with the unit vector, since they are parallel or in the same direction to the force. So we will get the unit vector using the position vectors. If we know the position vector that is parallel to the force, divided by to the magnitude of that position vector, so we can determine the unit vector, and we will use that unit vector to find the force. So again, this position vector is a vector that is always parallel to the force, and this is not a moment arm. A moment arm is the distance from the pivot to our force, which is this, the green one, and our position vector is blue, my diagram here. So to get the position vector will be, position vector is Rx I hat plus Ryj hat plus Rz k hat, and to get the magnitude, we will just get the square root of that, then Rx squared plus Ry squared plus Rz squared. So if we will solve now position vector, so that is R, and remember to get R, to get Rx, that is just what is the final position minus initial position of x, that is I hat, plus y final position on y minus y initial, and that is j hat, plus final position on z minus initial position on z, and that is k hat. So we will get the position points. So we have here position points on A and position of points of B that is parallel to the force of 500 Newton. So let's determine the position points on A. So this is the point. So it means that is 0 on X. And on Y, that is 3 meters. And on Z, that is 0. For B, the position point of B, so that is for B. So that is 4 meters on X. For Y, that is 0 and 0 on Z. Our position vector is 4 meters minus 0, so that is 4 I hat. For Y, 0 minus 3, so that is negative 3 J hat. And 0 minus 0, so that is 0 K hat. And the unit of that is meters. And to get the magnitude of this position vector, the magnitude is the square root of 4 squared plus 3 squared is equal to 5 meters. And to get the unit vector now of our position vector, so that will be 4 I hat minus 3 j hat divided by 5 meters. So this is the unit of this is meters also. So we will cancel out the meters. So that is 4 divided by 5. So that is 0.8 I hat. 3 divided by 5. So that is negative 0.6 K hat. So this is now our unit vector. So let's try to solve now for our force. So that will be, our force is equal to 500 Newton times 0.8 I hat minus 0.6 j hat. So that will be 500 times 0.8. So that is 400 I hat. Then 500 times 0.6. So that is negative 300 j hat. And the unit of that is Newton. This is now our force. And for our moment arm, so this is the distance from point O to our force, and that is only 4 meters along X. So that is 4 and I hat, and the unit of that is meters. So let's try to solve the product of this to get the moment. So to get the moment of force, so that is moment arm cross the force is equal to, this is I, this is J, this is K, and this will be 4 meters, 0, 0. And this will be 400. This is negative 300. And this is 0. So it will be, we will cover the I first. So 0 times 0, so that is 0. 0 times negative 300, so that is 0. I hat. Minus, we will cover this. So 4 times 0, so that is 0. 0 times 400, so that is minus 0. That is J hat. Plus, so we'll cover the K, so that is 4 times negative 300, so that is negative 1,200. And minus 0 times 400, so that is 0. And that is K hat. So for the moment of force here, that is negative 1,200. And the unit of this, so for R, that is meter again. And for the force, that is Newton. So that is, okay, remember K hat, the direction is K hat, and the unit is Newton meter. So this is the direction of the force of this problem.